I want to start today with a sound. It's a sound that's so ubiquitous, so everywhere, that your brain has probably just learned to filter it out.
It's the white noise of the city, really.
It is. It's that low, steady, mechanical hum you hear when you walk across, a parking lot behind a strip mall.
Or the top floor of a parking garage. Always there.
Exactly. We look up at a skyline and we see the architecture, the glass and steel. But if you look down, specifically at the flat roofs of, say, a grocery store or an office park, you see where that hum comes from.
It's a whole industrial landscape up there.
It really is. Acres of gray roofing just covered in these beige metal boxes.
And we usually just ignore them. I mean, honestly, unless you're a technician, you should be ignoring them.
Right.
If you're noticing one, it probably means it's broken.
But today, we're not ignoring them. We are doing a deep dive into the world of commercial HVAC. And before you think, oh, this is going to be dry, I want to be really clear about what we found in the source material.
It is surprisingly high stakes.
Very. We're looking at a technical training module for skilled trades, the 2025 edition on rooftop units. And what's inside isn't just a repair manual, it's this hidden world of physics and strict logic gates and life safety systems.
All operating in the background, yeah. I mean, you peel back the metal panel on one of these things and you find a machine that is constantly making autonomous decisions.
Decisions about what?
About preventing explosions or stopping poisonous gas from getting into the building or just managing massive amounts of energy.
So our mission today is to decode that choreography. We want to understand the sequence of events, the literal checklist that one of these machines has to run through every single time a thermostat clicks in an office.
Yeah, it's a lot more than just switch on fan spins.
Okay, so let's start with the basics, the geography. Why the roof? I mean, these things are heavy, they're exposed to the elements. Why not just stick them in the basement?
You could. And in huge skyscrapers, they often have entire mechanical floors. But for your average big box store or low-rise commercial building, it all comes down to one thing: real estate value.
Cost per square foot.
Exactly. If you run a retail store,
Yeah.
every single square foot is for inventory. If you have a restaurant, it's for tables. You don't want to give up, 400 square feet of prime space just for a big noisy heater.
So you banish it. You put it on the only free real estate you have, which is the roof.
Right. And that's what led to the package unit. That's the term the source uses.
Yeah.
Your house probably has a split system, furnace inside, AC outside.
Right.
But on a roof, everything is packaged into one box. Heating, cooling, ventilation, it's all there.
The RTU.
The rooftop unit, it's the workhorse.
Now, the training module makes a really sharp distinction right away. You've got the RTU, which is mostly about comfort, right? Recirculating air.
Mm.
But then there's this other box, the MAU, that looks almost the same but does something totally different.
The makeup air unit. Yeah, this is a really critical concept.
Yeah.
An RTU is about conditioning the air that's already there. And MAU is about replacement.
Replacement. So something has to have been taken away first.
Let's use the example from the source. A commercial kitchen. Think of a busy restaurant. You've got grills, fryers, all going full blast.
And those giant silver exhaust hoods are just roaring.
Roaring is the right word. Those hoods are like industrial vacuum cleaners. They are sucking out smoke, grease, steam, but they're also sucking out thousands of cubic feet of air every single minute.
And you can't just take air out of a sealed box. Something has to come back in.
Or you create what's called negative pressure.
What does that actually feel like? Would I notice it?
Oh, absolutely. Ever try to open the front door to a restaurant and it feels weirdly heavy? Like you have to really lean into it.
Yeah, I just figured it was a heavy door.
It's usually not the door. It's the building literally trying to suck the door shut because the pressure inside is lower than outside.
That's wild. Is it dangerous?
It can be, yeah. It can cause carbon monoxide to backdraft from water heaters. It can even lower the oxygen levels in the kitchen.
So the makeup air unit's job is to just force fresh air back in to balance the equation?
Exactly. It makes up for what the exhaust fans took out. And the tech inside these is aggressive. The source talks about direct-fired units.
That term jumped out at me, direct fired. It sounds kind of raw.
It sounds terrifying when you read how it works.
Yeah.
In your furnace at home, there's a heat exchanger. It's a metal wall. Fire on one side, air you breathe on the other.
Yeah.
They never, ever touch.
Of course. You don't want to breathe exhaust.
But in a direct-fired MAU, there is no wall.
Oh.
The gas burner is sitting directly in the stream of fresh air being blown into the building.
Wait, hold on. So the flame is literally touching the air that the chef is about to breathe.
Yes.
You're breathing combustion byproducts. How
Right.
is that remotely safe?
Or legal.
It's all about the math. It comes down to dilution. The unit is pulling in such a massive volume of fresh air that the ratio of fresh air to byproducts is something like 100 to 1. It's so diluted it's completely safe,
Wow. Okay. So the solution to pollution is dilution in this case.
pretty much. And the upside is it's incredibly efficient. 100% of the heat goes right into the air.
That makes sense. The source also mentions a much more critical safety role for these, specifically in parkades, underground parking garages.
Yes, this is where we get into the interlock.
An interlock is
Yeah,
like a dependency, right? If A happens, then B must happen.
exactly. So a parking garage is basically a concrete box full of cars spewing exhaust. Carbon monoxide can build up to lethal levels, and fast,
So you have those CO sensors on the pillars?
all over the place. And when a sensor detects a spike, it sends a signal to a central controller. And that controller triggers a synchronized flush.
It's not just turning on an exhaust fan.
No, because that would just create the vacuum we talked about. It has to be balanced. So the exhaust fans kick on high, and at the same time, the makeup air units turn on to flood the garage with fresh air. They're interlocked. They have to work together.
It's amazing how much trust we put in these automated systems. You drive into a garage, you don't even think about the air quality, you just assume it's safe.
And it is safe because a machine is running a constant logic loop to keep you that way.
Speaking of logic loops, let's get to the next part. The source calls it the sequence of operation, but I think of it more as the choreography of fire.
It really is a dance, a very, very strict one.
Because I think most of us have this idea that heating is simple, thermostat gets cold, gas turns on, spark, boom, heat,
If you did it in that order, gas, then spark, you would blow the door right off the unit.
which is not ideal.
Not ideal. Gas is explosive. You can't just dump it in a box and hope for the best.
Yeah.
So the machine has to run this strict checklist of prove-it steps before it's even allowed to think about fire.
Okay, walk me through it. The thermostat in an office clicks. What is the very first thing that happens on the roof?
You'd think it's gas, but it's not. The very first thing is a fan, a small, specialized fan called the combustion blower.
And its job is just to blow air.
Its job is to pre-purge the chamber. It runs for maybe a minute before anything else happens, pulling fresh air through the heat exchanger and out the chimney.
So it's clearing out any stale gas or fumes from last time.
Exactly. It's housekeeping. Get the room ready so you don't have a small explosion on ignition.
Okay, chamber's purged. What's step 2?
Step 2 is the first prove-it step. The control board has to know for a fact that the fan is actually working. It can't just assume.
Because the motor could be dead or a bird could have built a nest in the chimney or something.
Precisely. So there's an air-proof switch. It's a simple little pressure switch. When the fan spins, it creates suction, and that suction physically pulls a little diaphragm to close the circuit.
So no spin, no suction, no close switch.
And the whole sequence stops dead. It's a hard no-go. The system will just sit there and wait rather than risk opening the gas valve.
Okay, but let's say the fan works, the switch closes. Now do we get fire?
Now we get ignition. Most modern units use what's called direct spark ignition, which is basically a big spark plug. It starts zapping, and at the same moment, the gas valve opens.
And poof, we have a flame.
We hope, but hope is not a safety rating. The system has to prove instantly that the fire is actually lit.
This was the part of the manual that just amazed me. I assumed it would be some kind of heat sensor. If it's hot, there must be fire.
Heat is way too slow. By the time a sensor got hot enough, you could have filled the chamber with unburned gas. You need to know now. So they use a flame rod.
A flame rod. It sounds like something out of a video game.
It's just a simple metal rod that sits right in the path of the flame. And here's the cool physics part. The control board sends a small electrical voltage into that rod.
It's electrifying the fire.
Yes, because of flame. It's a plasma. It's full of ions. And because of those ions, a flame actually conducts electricity.
No way. So the fire itself becomes part of the circuit, like a wire.
Exactly like a wire. The electricity flows from the rod through the flame to the metal burner, which is grounded. The board is looking for that tiny little microamp current. If it sees the current, it knows, okay, the flame is bridging the gap. Fire is confirmed.
And if a gust of wind blows the flame out for a second,
The wire is broken. The current stops instantly, and the gas valve slams shut in a fraction of a second.
that is just so
Right.
clever. Using a fundamental property of fire itself as the safety switch.
It's basically foolproof. If the rod cracks or the wire breaks, it fails safe. No current, no gas.
There was one other safety mentioned for heating, the rollback switch. That one sounded pretty serious.
That's your last line of defense. Say the chimney is partly blocked, but not enough to trip the air switch. When the burner's light, the flames have nowhere to go, so they roll back out of the front of the chamber.
Toward all the wiring and controls. That's a huge fire hazard.
Massive. The rollback switch is a little thermal fuse right above the burners. If it feels that escaping heat, it trips and kills all power to the unit. That's usually a hard lockout. A technician has to come and reset it.
It's just this incredible chain of command. Every component has to do its job perfectly.
And that same level of protection applies when we switch over to cooling.
Right. Let's talk about the summer. The source goes over the basic refrigeration, loop compressor, condenser, all that. It's basically the same as your home AC or your fridge, just bigger.
Same physics, different scale. The compressor is the heart of the system. But what's interesting in these commercial units is how they protect that heart.
I saw a component listed called a crankcase heater, which seemed totally backward to me. Why are you heating the air conditioner?
It does sound wrong, doesn't it? It solves a very specific problem with chemistry. Refrigerant and oil, they're miscible. They love to mix together.
Yep.
So when the unit is off on a cool night, the refrigerant vapor in the pipes condenses back into a liquid, and it naturally migrates to the coldest, lowest point in the system.
Which is the compressor sitting in its pool of oil.
Right. So you end up with the compressor sump full of this liquid refrigerant and oil soup. And compressors are built to compress gas. If you try to compress a liquid,
You break it.
you destroy it. It's called slugging, and it will shatter the valves inside.
So the heater's job is to...
The crankcase heater is a little electrical band that wraps around the compressor, and it stays on when the unit is off. It keeps the oil just warm enough to boil any liquid refrigerant back into a gas, so the compressor is safe to start.
It's like an engine block heater for your car on a cold day.
That's the perfect analogy. Now, before we leave cooling, we have to talk about the economizer. The source really highlights this, and for good reason.
This felt like the biggest aha moment for efficiency in the whole document.
It is the unsung hero of commercial HVAC. Think about this scenario. It's a beautiful fall day. It's, say, 55 degrees outside. But inside a busy office, you've got hundreds of people, computers, lights. The inside of the building is actually heating up to 78 degrees. You need to cool it down.
Right, even though it's cool outside.
Okay, so you could run the compressor. That's the big power hog. It uses a ton of electricity.
Or you could just open a window.
That is exactly what an economizer is. It is a set of robotic motorized dampers. Instead of recirculating the hot indoor air, it closes that path and opens a damper to the outside, pulling in that free, cool, 55-degree air.
Then the power-hungry compressor stays off.
Completely off. They call it free cooling. You're just paying to run the fan. The source says this can save up to 90% of your cooling energy costs in the right climate.
That is huge. And it really makes you realize how kind of dumb our home systems are. My AC just knows on or off. It doesn't check the weather first.
That intelligence is what defines commercial systems. And that brings us to the brains of the operation, the controls.
Segment 4, the wiring and the logic.
Right, this is where it all comes together. It starts with the nameplate on the side of the unit. That tells the electrician the voltage, the power requirements.
And the source made a big deal about the disconnect switch.
Oh, it's a critical safety rule. You have to have a power shutoff switch within inside of the unit, and usually within 3 meters.
Why so specific? Why not just use the breaker in the basement?
It's for the technician. It's a line-of-sight safety thing. If I'm about to stick my hands into a fan assembly, I need to be able to physically see that the power is off. I can't trust that someone won't just flip a breaker downstairs by accident.
It's the don't kill the repair guy switch.
Basically, yes.
Oh.
So from there, we get to the part we all see, the thermostat.
The little box on the wall. But there's a whole language behind it, isn't there? The letters.
A color-coded language. R is your 24-volt power. W is for heat. Y is for cooling. G is for the fan.
I thought it was cool how the source showed the evolution of the wiring. It's like watching the system get smarter.
It is. The earliest systems were just 2 wires, R and W. The circuit closes, the heat turns on. That's it.
Then we added G, the green wire.
Right, for manual fan control. So you could circulate air even if you weren't heating or cooling.
And now we're up to, what, 5-wire or even 7-wire systems?
And that's where you get 2-stage heating and cooling.
What's the benefit of that? Why not just turn it on full blast when you need it?
It's all about comfort and humidity control. Let's say it's just a mildly warm day. A single-stage unit will blast you with 100% cold air. You'll get chilly, it'll shut off. Then you get warm, it blasts you again. It's very jarring.
Like driving in stop-and-go traffic.
Perfect. A 2-stage unit is smarter. Stage 1 might run at only 60% capacity. It's quieter, And this is key, it runs for longer periods.
Why is running longer a good thing?
Because a huge part of air conditioning is dehumidifying. The longer the air passes over that cold indoor coil, the more moisture gets pulled out. So a two-stage unit gives you a much more comfortable, less clammy environment. It only kicks into 100% power when it's really, really hot outside.
So it's a difference between flooring it and using cruise control.
Exactly. But even that 7-wire thermostat is becoming old tech. The source points to the real future. Direct digital control or DDC.
Building automation systems, BAS. This is where we leave physical wires and enter the world of software.
Totally. With DDC, you stop thinking about simple on-off switches. You start thinking in terms of inputs and outputs. The building have a nervous system.
So what's an input in this context?
An input is a sensor. It's a building telling the computer what it's feeling. Temperature, humidity, CO2 levels, air pressure in the ducts, and their analog inputs.
Meaning they're not just on or off.
Right. An analog input can measure a whole range.
Yeah.
It doesn't just say hot. It says the temperature is 72.4 degrees. It paints a full picture.
And the output is the action.
The output is the command. Open the fresh air damper to 45%, ramp the fan up to 80% speed.
And why is that so much better than a smart thermostat?
Because the logic can be infinitely more complex. A DDT system can know, okay, the building is getting warm, but I also know that electricity is most expensive between 2 and 5 p.m., and I see the outside humidity is dropping, so I'm going to pre-cool the building now using a different strategy.
And the building manager can see it all on a laptop from anywhere.
And track everything. You can spot a motor that's about to fail because you see its energy draw slowly creeping up on a graph over winks. It changes maintenance from reactive to predictive.
Wow. So we've gone from this big, dumb metal box on the roof all the way down to the ionization of a flame and then back up to software code running the entire building.
It's a heck of a journey for a beige box that most people never even look at.
It really is. And I think the big takeaway for you listening is that we take our indoor environment for granted. We walk into a building and just expect it to be comfortable and safe.
We feel the result, but we never see the process. We don't see the pressure switches and the flame rods and the dampers all doing their jobs second by second.
It's not magic. It's this incredibly robust engineering.
It's layers and layers of logic and safety.
And I want to leave everyone with that parquet example again, that idea of the interlock.
It's a powerful one.
The next time you drive into an underground garage, just take a moment. You're entering a confined space that is actively being filled with poison. And the only reason you're safe is because a silent, invisible system is constantly sniffing the air for you.
A life safety system that asks for zero credit.
You'll never meet the person who programmed it. You never see the code. But we put our trust, our lives in that system every single day.
Stay curious.
Thanks for listening. We'll see you next time.